let's talk about some exponent rules. We will talk about the rule, then we'll go work an example or two, and then we'll come back to the rules and we'll kind of go back and forth like that. Before we really get going on this, I want to review real quick. When you have an exponent, one of the terms we use is a base. That's this guy. If we have a to the b power, whether a is a variable or a constant, it's the big one. That pen is way too large. Could be a variable. Could be a constant. A constant being any number that you know about. The other part of this bad boy is the exponent. It's the little bitty number up in the air that tells you how many times to multiply the base times itself. How many times to multiply the base by itself. The only other thing that might get added to this could be a number out in front. If there was a number out in front, this guy would be the coefficient. It's the number, not the hashtag. Not the exponent. The number in front of the base. And usually if there's a number in front of the base, this is going to be multiplication attaching them. So there's the vocabulary that we're going to get out of the way. Now let's go up and talk about some rules. Adding and subtracting like bases. That means if you have 2x squared plus 3x squared. Our bases are the same. Our exponents are the same. So regardless of whether this is adding or subtracting, we are going to put the constants together, and we're going to leave the base and the exponent the same. So we end up with 5x squared. Do not ever, 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 ever change the exponents on these. Never change the exponent. Only combine the coefficients. So I'm going to go back here. Exponents and multiplication. Looks like I'm going to make up a couple of my own. So I'll come down here and I'll make up a couple. Maybe we have 3x to the fourth plus 2x to the fourth. You check to see if the bases and the exponents match. Combine the coefficients. The base and the exponents stay the same. If you happen to be subtracting, maybe we have 2x squared y minus 3x squared plus 4x squared y. I threw in a little bit extra here. We have 3 different terms. We can only put together the ones that have matching variables and exponents. So I have an x squared y and an x squared y. This guy is the odd man out. We don't have a base or an exponent that matches anywhere else. Some people would say, but Ms. Graham, look, there's the x squared right there. You're right, but in order for the bases to match, we would have to have the y in that middle term. So what we can do is combine these two. We pull out the coefficients and combine those. Leave the exponents and the bases the same. And then that guy we couldn't use, the 3x squared, we're just going to bring him down by himself. We'll clean it up a little bit. You probably learned something like this when it comes to combining like terms. Some people have a tendency to play with the exponents. Don't do it. Leave the exponents alone. Now these, I know it's there. When you are multiplying like bases, you add the exponents. Every single time. So if you had a to the x power and a to the y power, the a's match. So this would be a to the x plus y power. Now, if you're not a formula person, buckle your helmet, because here we go. If I look at number 1, I do have matching bases. My 4's match. And the rule says when you have matching bases, add up the exponents. So this becomes 4 to the 2 plus 2 power. So it's 4 to the 4th power. 4 is a little more complicated. Your first instinct is to look at this first 2 and say, oh, there's not an exponent there. Well, literally there is not an exponent there. But we have been through this before. We've talked about math people being ridiculously lazy. And if we don't have to write it, we're not going to. So when you see a base without an exponent, it's understood that that exponent is a 1. We do have like bases. All of our bases are 2's. So this means we would have 2 to the 1 plus 2 plus 2 power. And that's the same as 2 to the 5th power. Could we go plug these in the calculator? Absolutely. But right now we're really just interested in taking care of these exponents and where they come from. So we're not going to simplify these completely. I'm going to jump down here to number 5. Remember, we're only interested in matching bases, so we only care about the ends. It doesn't matter that we have a 2 and a 5. We're going to pull the 2 and the 5 in front like we did with the adding and subtracting. And then we have n to the 4th times n to the 4th. Well, I know 2 times 5. 2 times 5 is 10. And I have n to the 4 plus 4. Be super careful right here. A lot of people would put 10n to the 16th because they multiplied the 5 and the 2, so they kind of want to go multiply the 4 and the 4. Don't do that. You add the exponents when you multiply like bases. We'll do another one like that. Again, I have an r and an r, so I have like bases. I don't have an exponent written on that first r, so I'm going to write in a little 1 just so I don't forget about it. I'm going to multiply the coefficients. I'll put the r's next to each other. The commutative property of multiplication says we can do that. 6 times 5 is 30. Oh, goodness. I got a little bit ahead of myself. And this becomes 30 to the r times r cubed. Let's see if there's anything else. Oh, yes. So we're going to up the ante just a little bit. We made it a little bit bigger, but that's okay. Now, one of the ways you may want to do this when it comes to writing it out and until you get used to the patterns, go ahead and pull your coefficients out in front again. So we would have 7 times 10 times 8. Now, we have to put these together. I'm going to pull my u's. I have 3 u's and 1 more. Then I'm going to go get the v's. I have a v to the 3rd and a v to the 5th and another v to the 3rd. If you're struggling a little bit with the idea of adding the exponents, I'm going to do this one a little bit differently so you can see the mechanics behind what we're doing. 10 times 8 is 80 times 7 is 560. Now, a long time ago, you learned that u cubed meant u times u times u. And then I need a u to the 1st. So this guy goes with these. That one is going to go right here. Then I'm going to do similar things with the v's. So I first need, oh goodness, 3 v's. And then I need 5 v's. And then I need 3 more v's. So I'm going to go count. I still have 560. I have 1, 2, 3, 4 u's, so that's the same as u to the 4th power. And then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 v's. So that's what we're really doing. If I go and add up my exponents, 3 plus 1 would give me 4. So that checks out. And then if I do the v's, 3 plus 5 is 8, 9, 10, 11 on the v's. So that's the process we're following. It's just shorter to use the rule. We'll do one more of these without the parentheses. We're going to save the parentheses for when you're a little bit older. I'm going to run down to 20. No, I'm not. I'm going to do 18 because I like that one better. I picked 18 for 2 different reasons. The first reason is that the first chunk right here appears to be missing a coefficient, but it's not. I picked this one because I want to remind you that if you don't see a coefficient in the front, you can always put a 1 there. It's like the exponents. If the exponents appear to be missing, they're really not. They're just 1s, so you have to remember to write them in. So now I'm going to multiply 1 times 4. I have a u to the first and a u to the first. And then I have a v to the first and a v to the fifth. I'll do it both ways just in case. So I'll get u and 1 v and 5 more v's. So this is 4u squared, 1, 2, 3, 4, 5, 6, v to the 6th. The other way would still leave u the 4. We would have u to the 1 plus 1 and v to the 1 plus 5. So there's both approaches. Regardless of which road you decide to take, you end up at the same destination. So now let's go back up. I'm sorry if I'm making you a little dizzy. We're going to look at dividing like bases. But before I tell you that story, I have to come down here and tell you this story. So here's the catch with negative exponents. Any variable or constant with a negative exponent has to be switched to the opposite side of the fraction line in order to become positive. So, if I happen to have 1 over a to the negative 1, that means the a or the, hold on, this part would go to the top, the 1 would become positive, and we'd be left with a 1 in the denominator. If you think about these in terms of fractions, it gets a little bit easier and you think about just flipping it to the other part of the fraction. Remember, you can always make a number a fraction by putting it over 1. The other thing you need to be super aware of is if you have a coefficient with a negative exponent on the variable, here's what happens. Remember that this 3 has its own exponent. It's got a little 1 sitting up there. I'm going to change the color of it so it stands out. So if I were asked to write this without any negative exponents, I would start with my fraction bar. Because remember, I could put 3x to the negative 2nd power over 1 and make it a fraction. And I'm going to look at it piece by piece. If I look at the 3 first, it has a positive exponent. It has a positive 1, so it gets to stay where it is. This guy, the x, has a negative 2 for an exponent, so it has to switch sides of the fraction. That's what we're looking for when we ask you to write something with a positive exponent, and you'll get some extra practice with that in just a minute. So now let's go look at dividing like bases, and these go together, so we'll do examples of them together. When you divide like bases, when dividing like bases, subtract the exponents. Usually, this is going to look like maybe x to the 4th over x to the 5th. So what we want to do, we're always going to do the top first. So we would do x to the top exponent minus the bottom exponent. So it would be x to the 4 minus 5. Let's set that rule so that we're all talking about the same thing at the same time. X to the top minus the bottom. That way we all end up in the same place. So I am going to mosey down here. We're going to skip the parentheses ones until you're older. We're going to look at exponents and division, and we're going to start out easy. I do want you to notice that our answers can only contain positive exponents. That's why I told you the negative exponent story before I told you the dividing story. So we're going to start out small. We have 5 to the 4th power divided by 5 to the 1st power. And notice it's 5 to the 1st power because we write in our little imaginary 1. So this is going to be 5. Remember, we're going to do top minus bottom to the 4 minus 1 power. So this is 5 to the 3rd power, and it's a positive 3, so we don't have to try to rewrite it to get the positive exponent. The positive exponent already exists. So we'll look at 2. The first thing I notice is that I need a little 1 for the 3. That means my 3 has a 1 for an exponent. Then I'm going to do 3 to the top minus bottom, so this would be top minus bottom. If it makes you feel a little bit better, we can go ahead and put this over 1 so that we have a fraction, since we started with a fraction. 3 to the 1 minus 3 means we have 3 to the negative 2 power over 1. Now we can't leave it like that because the directions say to contain only positive exponents. So what that means, so I'm going to start with my fraction bar. The 3 is a negative exponent when it's in the numerator. So I'm going to flip it down to the denominator. It becomes a positive exponent. And we leave the 1 on top. So here's what we're going to do with this one. This one is a little bit different because our variables or our bases have coefficients. We are going to treat these coefficients just like they're a separate fraction. I could rewrite this fraction as 3 over 2 times r cubed over r squared. So then I'm going to see if I can simplify the 3 over 2. Well, the only way to simplify 3 over 2, and by simplify I mean reduce it to lowest terms, I could write it as 1.5, but that's really not going to help. So I'm going to leave it as 3 over 2. Then I'm going to take care of my r's. I'm going to do r to the third minus 2. Top minus bottom. So I'm going to put in my 3 over 2. 3 minus 2 is 1, so I just have an r left on the top. We'll go down to number 10. I'm going to peel this fraction off the front like I did in the first one, or in the last one. So I can rewrite my fraction as 10 over 6 times p to the 4th over p to the 1st. When I go look at this fraction, I know I can reduce that by 2's. So that fraction out in front becomes 5 over 3. And then I have p to the 4th minus 1. My 5/3 stays the same. 4 minus 1 is 3. I'm going to go back and put these over 1. So I maintain the image of the fraction. Once I'm finished, I can put my pieces back together. And this becomes 5p cubed over 3. There's one on here that's a little bit different, so I'm going to take a look at it. I'm going to peel off the coefficients again and write this as 8 over 10 times m cubed over m cubed. Now, about a bajillion years ago, you learned that any time you have something over itself, you get a 1. Well, here's why. I'm going to apply the same rules that we just had. So if I reduce the 8 and the 10, it becomes 4/5. And this becomes m to the 3 minus 3 power. Well, 3 minus 3 is m to the 0 power. And it feels like maybe when you were younger, maybe last week, we talked about anything to the 0 power is a 1. So this becomes 4/5 times 1 over 1. So that is simply 4/5. That is why anything to the 0 power is 1. Now this can become a little more complicated when we add extra variables. So I'm going to keep using the subtraction version. For those of you who are very visual in your learning, I'm going to write it out too, and you can kind of choose which method you pick. I'm going to separate out my fraction. I'm going to do x over x. So I get x to the 4th over x to the 5th. And y to the 7th over y to the 4th. 14 over 6, if I reduce by 2, I get 7 over 3. this becomes x to the 4 minus 5 and y to the 7 minus 4 because we're still doing top minus bottom. So I get 7/3 times x to the negative 1 over 1 and y cubed over 1. But I can't leave that negative exponent. My 7 and my 3 are okay. They both have positive exponents. My y cubed has a positive exponent. I have to take that negative 1 sitting up there on the x and bring him down here to the denominator of the fraction. That changes his exponent to being positive. I'm going to go up here and I'm going to show you another way you could think about this one. I'm going to factor everything out. So I really could rewrite this as 2 times 7 with 4 x's and 7 y's. I can write 6 as 2 times 3. Five x's and 5 y's. And then I'm going to use the idea that anything divided by itself is 1. So these can't write with the erasergram. Those 2's make a 1. Those x's and those 2 x's and those 2 x's and those 2 x's all make 1's. Those 2 y's make a 1. All of those make a 1. So what I'm left with, since 1 times anything is the anything, is a 7 on the top and a 3 on the bottom. Then I have 2 y's, and then in the denominator, I have an x. So either way, we end up in exactly the same place. It just depends on what route you take to get there. I recommend you pick the one that works for you and stick with it. I think we will go back up. We're going to save a power raised to a power for when you're a little bit older. We did talk about 0 exponents. Again, I think it was last week, but we can briefly put it in here if you would like it to be complete. So anything to the 0 power is 1, and a is any number that you can think of. I'm going to flip through very quickly. If it makes you dizzy, close your eyes for a second. Make sure we hit everything I wanted to hit. I do believe so. We'll save the rest for another time. If you have questions, please come by to see me or send